Hi,
Martin.
thank you. Thank you, Andrew. Can you hear me?
Yeah, I'm just going to introduce you, Paul.
Okay, great. Thanks.
Yeah, Paul Martin, ESEP, is the owner and president of SE Scholar, LLC, where he teaches an online INCOSE ASEP CSEP exam preparation course. He's been teaching this course since 2009 and has taught several hundred students. Paul is also a practicing systems engineer with over 35 years of experience. He has been everything from a product engineer for General Electric product division to a software systems engineer for a multi-million-dollar Navy program. Presently, he's supporting a government agency's portfolio management office, helping them with architecture alignment amongst hundreds of programs. Paul has been involved with INCOSE since 2000 and has served on the local INCOSE Chesapeake chapter board of directors as programs director and communications officer. Paul also serves as an adjunct professor for the University of Maryland, Baltimore County College of Engineering and Information Technology, systems engineering graduate programs where he teaches ENEE 663, System Implementation, Integration and Test, and ENEE 667, Advanced Systems Engineering Processes. He is also a senior member of IEEE. Paul, the virtual floor is yours.
Thank you so much, Andy. I appreciate this opportunity, actually. I really appreciate the INCOSE CAB organization being able to make this opportunity available to me. This actually is a part of a lecture that I provide my students for one of my courses at UMBC. It's one of the ones that I finished the course up with, and it's just a way for me to impart into my students what to expect in the profession that they are, involved in as we go forward. Okay, next slide. One of the things I appreciate, and one of the things I really want to put forth in this lecture, and I hope you, if you take anything away from it, is that I really want to encourage you to think of system engineers more as problem solvers. As a matter of fact, John Thomas, our INCOSE president, actually put out a really good paper called Why System Engineers Are Essential to Your Organization. And in there he said, across an organization's products or services, system engineers also provide that critical leadership for integrating the technical activities. They have skills to influence the multidisciplinary teams to reach consensus on how a system solution should come together. As problem solvers, they focus on outcome, not process. I think it's important that we understand process from a system engineering point of view, but it needs to be a process that's involved with value and that it gives value to the organization. Let me step back from system engineering for a second and just ask you, how was your morning? Did you wake up in a nice warm bed, a nice warm house? Did you shower? Did you even think about where that water came from? Did you perhaps take a jog or something in the morning and listen to your iPad or iPod, as you're running through, and think about the actual aspects of that iPad or pod, being able to get music and stuff on your, so that you could run and so you could jog, or coming back and getting food preparation. Where did the food get into your refrigerator and how did that come about? All that aspects, the transportation to get to your work, the gas aspects, the actual communication in line, being able to communicate, everything you do on the computer at work in order to communicate into the internet or with your peers. All those things that occur are because we're in a man-made world, and you are absolutely embedded in that man-made world. Everything you touch is through this man-made aspects of it. And the interconnections, the more and more you think about it, the more and more you understand that, wow, everything that we are touching is all interconnected. This is an important aspect of understanding what technoscience has done for us, this science-linked technological innovations. When you think about something as early as the electric telegraph, which occurred back in the 1840s, it had to be invented and actually demonstrated because of scientists, physicists, were able to show that this phenomenon could be captured and utilized. The same, taking that technology and being able to do an undersea cable. They actually tried to put one in the early 1860s, but it failed within a few months after millions of dollars of putting it together. And then physicists had to come in and redesign it so that it would last for almost decades. But it only because they had to understand the properties of the science that was involved. Think about electricity, all based on theories that came about from the 1830s, or even radio technology, all from mathematical theory of electromagnetic field from the 1860s. All these from the 19th century going into the 20th century, slowly building up, I think, over the 100 years here in order to arrive at what we have today. And even during that time, in the 20th century, we've seen some really large programs, the Manhattan Project, which had to occur within a few years to create the atomic bomb, or the space program to put a man on the moon back in the 1960s. All these things were well done, large engineering projects that were successful. And there's basically a reason for that. All these technologies were new, but the science that was used was well understood. And there were clear requirements in terms of what needed to be built and what needed to be done. And the design to accomplish that mission was designed from scratch. They didn't have to worry about too much about the infrastructure and other things. They could design them from scratch. Even with these large engineering projects, with everything it has, we still have projects as we get closer to modern day that actually fail. These are projects like the IRS tax system modernization project back in the early and mid-90s. $48 million spent towards that, and it was scrapped. The London Ambulance Service computer system, even though it was a few million that was spent on that, 20 lives were lost because of that failure. FBI virtual case file in the early 2000s had to be scrapped because it was unusable, and the same with the DoD expeditionary combat support system had to be scrapped even after $1 billion worth of work. What is it? and you think to yourself, wait a minute, we were able to put a man on the moon, and we can't get an ambulance system to work? So there is an issue that I think we're running up against, and you'll see this as you look at the history of technology, this whole aspect of projects becoming more and more complex. You have this interdependent subsystems. And you bring in the law of requisite variety, where the larger the variety of actions available to a control system, the more permutations can occur, and how does it compensate for that? And all through that, how do you test every function within the interactions of a complex system? And then you winding up with these unanticipated emergence effects. Actually, emergence is one of the key aspects of complex engineering and patterns. You know, understanding where they're coming, that there's interactions between the parts where the parts don't really provide a clue of where these functions are coming from. It's only through that interaction. But when you have unintended consequences, you have unpredicted emergence. And really, if you think of emergence, it's the putting together of the entire system. It's your entire system's function versus the reductionist approach that even as system engineers and scientists, that we take to a complex system, we always tear it down in order to try to understand it better. But that's where we need some kind of science for system engineering. And system science is one of that approach that we need to think about. But so far, we haven't really seen something to impact the way we want to do system engineering. I think we need to get to that point, and we need to go more and more into what it takes to get to that point. Complexity. Now, I know you may have your definition of complexity,
this is great.
but there's no clear definition of complexity. Go ahead, I'm listening. Andrew?
I'm having trouble getting access to the Global Meet session. This is Greg Campo from the Michigan chapter.
Okay.
I'm wondering if anyone else is having trouble as well.
Are you hearing my voice? You're hearing my voice?
Oh, yeah. Yeah, I'm hearing you okay. Just I'm not on Global Meet with your voice. I guess dialed in directly to the phone.
Right.
So
Not sure.
I'm in Illinois. I can see the Meets just fine, as well as hear his voice just fine.
Yeah.
Okay.
So you may need to rejoin Global Meet.
Yeah, I'm on
sometimes that
right now.
Yeah. All right.
Huh. Okay. Thanks.
Okay. Oh, no problem. So with complexity, I know there's those in the audience that may feel they have a clear definition, but there are some that really look at complexity based on the branch of science that it actually is in, whereas others feel complexity should be a natural phenomenon. It doesn't matter what field. It should be a single science, no matter what type of system you're going after. And, which one is that clearly understood as we go forward. But complexity is something, and I'm going back here to what Albert Einstein, he says, make everything as simple as possible, but no simpler. But Professor Brian Collins just presented a wonderful system engineering brief at the last INCOSE symposium in Philadelphia. And then there he actually said he likes to think of it kind of this way, make everything as complex as possible. There's no more complex than it needs to be. So sometimes, well, actually, let's go to the next slide. I think the one way we try to deal with complexity is eliminate it. How can we go ahead and simplify our objectives? Or is there a way that we can come up with a more simplified version and then just add complexity to it through this evolutionary incremental development process that would work? And with that in mind, with the fact that we're always dealing with complexity, do we need to think about a new approach to system engineering? So what I wanted to go through with you is how INCOSE has seen system engineering in the future for 2020. And in that vision statement that they put out about 7 years ago in 2007, they talk about complexity can be considered as a measure of how well knowledge of the system's component parts explain the system behavior, and also by the number of mutually interacting, interwoven parts, entities, and agents. In other words, complexity should be measurable and should have a metric aspect of it. But let's go ahead and dive a little bit deeper into this vision statement. And the way they've outlined it is they talk about systems and their nature, trying to understand, especially as future systems will get more complex. What about the system engineering environment in order to make new systems? The system engineering processes and models and model-based system engineering. So we'll get into each of those as we go along. So let's talk about systems and their nature. Basically, we want to think about their purpose and scope, complexity, system of systems. I actually am going to break out all 7 of these separately. So autonomy is an aspect of the purpose, scope, and capability of systems. There tends tends to be this trend that we're looking at more systems across the geography as well as increasing capability. So large systems, of course, are something that we're concerned about. But there's also this aspect of what about these increasingly small systems, microsystems, where they actually have to work within the environment they're in. So we have both those aspects of systems that are being done. Complexity is increasing because of components and interfacing. Creating solutions for these complex problems, of course, most likely you have a complex system going into that. Complexity is what attributes to program failures at times when you don't recognize the actual aspects of the emergent properties of what you're putting together. That's where all of a sudden the role of the system architect makes more sense, and that you want to make that more important, making sure you're architecting the system so it can take into account the complexity and the robustness it needs. System of systems, that's where you're taking independent systems and trying to achieve some kind of emergent behavior that each individual system isn't able to put together. Again, system of systems will start treading on the complexity aspects because you have this normally networks that are put together in order to make this system of systems works. And of course, understanding, designing, and managing the interfaces is one of the aspects to be able to get a hold of complexity. Technology that's actually used, advances in technologies, is something that we need to think about as we put into systems. These new technologies allow systems now to have what in the past we couldn't obtain in terms of purposes and capabilities. So they're definitely something that we need to be aware of and work. So these technologies, just to keep talking about that, is we're talking about computational power increasing, information storage increasing, miniaturization, biotechnology, connectivity and interoperability is increasing as well, and new technology within the system for integrated processes. As a matter of fact, part of that technology is this embedded software and information processing, as we see more and more of information technology becoming more of a service and trying to work within perhaps an open source type software environment. The roles of human as part of the system to have greater, a system should have greater autonomy, but you still need a human to direct and intervene where possible. So that's an aspect of system natures that we need to take into account. And then one of the more, at least from my experience, a little frustrating aspect is what do we do with the legacy systems, and how do we modify and update them so their life expectancy will increase? Now, this is all based on not so much what system engineers want to see, but the reality of the world and the way businesses go forth. They want to get their costs back, and so increasing a system makes more sense as we go forward. All right, now, what about system and natures in the future? So we're going through this Vision 2020, and what they talk about is just the fact that systems will exhibit this interconnectedness that will allow them to interconnect even autonomously as they go forward. And of course, you'll get more larger systems because of that, not just local systems, but they'll start going out regionally and even globally as they go forward. And then, of course, you're struggling to understand how to be able to bring in these new systems with the legacy systems that are already there, and try to come up with these system of systems with new and legacy as well. And then design for continuous adaptation, and the systems of future will continue to exhibit characteristics from the present trends we've already looked at. System architecture will become more important but it will not just be a technical architecture. It will bring in markets. It will bring in aspects of the needs of the customer and the enterprise and other frameworks. So architecture will have that, and that approach, they feel that 2020, that approach will be based on that emerging system engineering patterns and structures and having that automation work with it. And then you'll start getting more of this model-based system architecture as we go forward. Technology, where you're getting virtual devices and that human system interfacing will be more sophisticated and complex, and they will need to be integrated into these systems, especially from the control aspect. So developing these new capabilities resulting in that broad range of topics, be it embedded intelligence or allowing humans to complement a system intelligence, those are the type of things that we have to work through as technology increases. Okay, we talked about systems in their nature. Let's talk about system engineering environment, where we're at a current aspect, where present-day solution building is we're integrating products and process development, where developers consider the entire life cycle at the earliest stage. Just pretty much out of, if you read the handbook, System Engineering Handbook, talks to this. So this is the current state of system engineering. We're looking at government and commercial organizations recognize the importance of system engineering. So that's a trend we're slowly seeing. And we're also seeing international cooperation and collaboration in terms of standards. So 15288 is being updated fairly soon, very important as we go forward. And then the fact that you have multidisciplinary teams in different areas geographically and working together using the standards that are available is another aspect of the current state and trends of system engineering. There are some negative trends we need to be aware of. There is no agreed set of unified principles and models across the wide range of domains. A lot of people feel that system engineering handbook is mainly geared to perhaps DoD type industry and things like that. Whereas, what about commercial industries or the biotechnology industries? So that's where trying to get that those standards across multiple domains is something that we really need to push forward to. But there is this lack of consistency of education. I think that's being addressed as we try to come up with a comprehensive set of system engineering aspects that they need to bring through. Also, there's this aspect of balancing hardware to software and trying to figure out how people work within the system. Basically, what we're running into this core challenge of identifying and delivering value to every stakeholder as we go forward with system engineering. So within this document, Vision 2020, they feel the future system building environment will allow more interoperability, more collaborative tools that are broader range of application, more people-centric interfaces as they start working this. Actually, the tools will start incorporating those very technologies I was talking to you about before, how that will increase in terms of especially human-system interactions. Also, system engineering capabilities will be created to support the application of system engineering methodology in an agile, robust way. That way, you're getting more systems theory application involved. You're increasing the analytical methods and tools. You're advancing system engineering education so that you're getting more interdisciplinary integration as well as systems thinking as you're working forward. You're improving the integration of engineering specialties, understanding psychological, language, as well as cultural impacts to the stakeholders and to the requirements, and improve shared understanding of system engineering concepts among all the stakeholders. So improving that usability of standards through the harmonization of engineering project management and business processes for the future of system engineering is an important aspect of going forward. Okay, so we looked at both system engineering systems and their nature, system engineering global aspects of system engineering, global system engineering environment. Now let's look at system engineering processes and where they stand. And right now, that whole maturity and formation of formalization of system engineering process is good. We've got the standards, we've got our handbook available. However, there is this perceived aspect is there's this burdensome, heavyweight efforts of the processes that are involved and things like that. Also, the application of small, medium-scale enterprises is difficult and remains very weak, and we need to continue to push for the tailoring of the processes that are out there. And also the adoption is further impeded by the lack of lean or agile processes as part of the standards that are out there. The ugly part is that you have this whole aspect of major coherent system engineering processes that can be applied to multi-particle teams that's just not there and available. And the lack of lean, agile principles that could remove tasks that don't add value or provide this adaptability for an organization that needs that ability is missing. So that's the good, bad, and ugly. Basically what it comes down to is how difficult it is to do these complex systems using this subsequent requirements predicted models of practice. So that's where we are currently with our processes. In this document that INCOSE put out, this Vision 2020, they feel that their core challenge is to deal with this accelerating change of both the user needs as well as your external environments as you start putting more techno-scientific aspects into it, the technology that's being embedded in our infrastructure. So they feel by 2020, we should be fully supporting concurrent system engineering systems, allowing technology to be inserted to accommodate those rapid acceleration of technology changes, enabling future systems to take advantage of emerging technologies by effectively integrating those technologies, as well as the legacy systems and advances that are already out there that we will have to work with. And your success criteria will be the whole aspect of understanding that interoperability and the resilience that technologies and interfaces will bring to the table. So that's actually a way that we can actually measure. We'll focus on processes that only add value, be very intelligent in our engineering environments, be able to better plan and control through workflow management processes, better decision-making, and, of course, being effective in our logistics and maintenance support infrastructure. Also, we want to see the state of the best practices in system engineering be actually well codified, and that we'll have this continuous process improvement. It'll be something that's widespread. Coordination and harmonization of these processes between disciplines and businesses, it would be good to align those, be able to understand and align stakeholder values. The reduction of risk through process simulation and sensitivity analysis is very important. And the robust strategy of integrating coherent human, social, technical concepts. Now, one of the last things that this Vision 2020 talks to is model and model-based system engineering. There's a reason they're going to do this. We'll talk about that in the next, near my last few slides. And we'll actually talk about why model-based system engineering is so important. But currently, we kind of got a model-based system engineering that's out there, but it is kind of practiced ad hoc. It's not integrated with the other processes just yet. I think we're making tremendous strides on this. Remember, this is a 7-year-old document, so some of the things they were worried about and some of the visions that they were hoping to have, I think, are coming to pass. Especially when it comes to model-based system engineering in the future, they felt you should have a modeling language that's very domain-specific. Now, that we're not at just yet, but I think we're working towards that. And, of course, having standards with a firm mathematical foundation would give you that high-fidelity simulation and real-world representation. Very difficult to bring about. But in order to do that, you do need this reuse of model libraries, taxonomy, and design patterns, which means you kind of have to have businesses start and system engineers start sharing that. And sometimes businesses feel these are very important to their business and competitiveness. Sharing that may be a difficulty. But having standards in order to distribute your model repository and having this highly reliable, secure data exchange between the various published interfaces, very important to the key of making this work in the future. Now, what about future considerations as we're thinking this through and stuff? Even 7 years ago, I don't believe they were thinking of IT as a services cloud infrastructure. And how do you go about coming up with model libraries, taxonomies, or design patterns which is fine in an existing solution space, but what about where there are no existing solutions right now? And you have technology like 3D printing on physical prototypes. Is that something that will help us in our modeling as we go forward? Anything new for future considerations? They need to be created. They need to work in this vast, interconnected, man-made environment you woke up in, and that we all woke up in. And so we need to think about that in terms of how we're coming up with new systems and how they have to work in this man-made environment. Niels Bohr once said prediction is very difficult, especially when it comes to the future. And a lot of times it's difficult to do that because the problem hasn't arisen yet. And a lot of times these problems will arise because of the various aspects of incorporating new technology into our infrastructure. And all of a sudden a new problem will arise and we'll need to solve that using system engineering principles. I pulled this out of how can we actually look at the future. How do we go into that? And actually, what was good about the INCOSE 2020 document is they actually did this. They looked at existing trends. They looked at trends to be. They extrapolated it as much as they could, assembled their scenario within the document, and then they backtest to see what had to happen in order to get there. I'm sure INCOSE is working on a 2025 version that they'll release in the next few months. You should be on the lookout for that, doing the same exact thing. How do we look at trends? How do we think about trends? And how do we figure out a way to influence the trends in the future? One thing that I'm hoping as we think about these future system engineering, that we move out of this management realm and into a holistic solution realm where you're taking more systems thinking into play, and we'll start taking on these large-scale global problems. Of course, one problem with these large-scale global problems is who's going to pay for them, who's going to be the sponsor of them. You still need that real-world aspect of how to go about this. But trying to come up with solutions on a global scale is something that I think for system engineering we should accept that challenge and start working. I think it's the best hope that we have. The other thing I would like us to start thinking about, and this, when you start using design thinking with this systems thinking component, design thinking is just standard system engineering where you define the problem, create and consider as many options as possible, refine those selected directions that you come up, repeat as often as you need to, and pick some kind of winner and execute that. That's design thinking that's in the commercial realm, and I think if they start using that with a systems thinking component, we would get to a better aspect of coming up with system engineering for multiple domains as we go forward. The other thing is how do we work through the emergence problems, especially unintended emergence or undefined emergence that comes about. And that's where modeling is the key to that. And I think for them to do a model-based system engineering is one of the things we need to continue to push forward as we do it. So I think I'm on time. I only took 40 minutes. And of course, I'm willing to take some questions as we go forward. Looks like we have about 4 or 5 of them.
Yeah. Paul, thanks for a great presentation. If you can look at the questions, there's been a very active chat line while you've been talking as well, but I think the majority of the points have been captured in the Q&A.
Great, great. Okay, so there's only about 5 of them here. They can't see the Q&A, right?
I don't think so. So if you can read out the name of the person who's asked the question and then the question or comments that they've made and then give your response.
Great. I'll definitely do that. So Brian Bernenbach, you stated that you viewed system engineering as problem solving. The implication is it's after-the-fact firefighter. That's actually a good point. And at one point in my presentation, I talk about the fact that problems come up usually after you implement things. But anyway, I think that a real value system is at the beginning to middle of the project, not after the damage has been done, and that is true. And I think that's what, for the future of system engineering, we need to be those ones that can predict the fire, right? So we can say not after the fact firefighter, but we need to be and I think if we can get, and I've been very fortunate to be able to see the new 2025 one that's vision that's going to come out. And one of the things they really push for in the new one is policy. How do you work in so that the policy people who are responsible for policy use system engineering type principles to try to work through the solutions of things? Because a lot of these system engineering solutions don't take into account the culture or the social aspects of what's being implemented. So it's very important that we work that. Okay, John Mulbearer, I think I said his name right. He goes, why not add the recent failure of government website? Oh, yeah. He's right. Okay, so he's talking about the fact that the Obamacare websites were a complete failure. And actually, it's interesting. I read an article just recently that one of the developers was actually a CMMI level 5. And you're like, what? And they still failed? So it's just that it kind of pinpoints to the fact where you could have all your processes into play, but if you don't have your stakeholders and their requirements completely understood, your processes mean nothing. So understanding the problem is step 1 of good system engineering. You said, and this is Robert Gilbert, we said you live in a man-made world. Do you think that that nature will remind us more in the near future how little she respects that view. And you're absolutely right, Robert. I think in the future, I think that's another stakeholder that we need to bring into play, especially as we start talking about these larger implementation of larger systems, that nature and environmental concerns need to be up front as part of our requirements. Okay, Sarah Sheard, a good friend of mine, she says, not so much a question as a point. I would argue that we have no means of dealing with complexity other than breaking it into parts and interfaces among it. Reduction is not bad. What is bad is selecting one view as the only view and then only breaking things up that way and not only describing the way that those pieces interact among many dimensions. Those dimensions included like power, signal, mechanical interfaces, data, protocols, timing, effects on user, change in the environment, development of costs, et cetera. Sarah's right. There's actually an aspect I forgot to bring up and I got this from the lecture I heard from the INCOSE seminar, where the professor talked about the fact that if you think about analysis is that whole reductionist, let's analyze the parts, tear it down and look at the parts, but where is the synthesis, when you actually bring the parts together and understand the emergent properties. So Sarah's right. I don't want you to think reductionism is bad per se, because it is the way we do our system engineering. But I think we also need to be very understandable about integration, and emergence needs to be something that we explore further. And I think we really need a better scientific foundation for us to work that. Okay, Robert Gilbert, do I have a little bit more time, Andrew? I should just keep going, right?
Yes, just keep going. You're doing fine.
Yeah, it looks like there are more questions coming up, so this is good. Okay, Robert Gilbert, he said, can you distinguish more clearly the difference between our current management realm, good point, versus the holistic solutions realm, particularly when it's meant by management realm? So when you look, one thing I think Andrew mentioned, I teach the System Engineering Handbook to students. What I really enjoy about 15288 and the System Engineering Handbook that INCOSE put out is the fact that it is contextual. I mean, it does say, look, you are not going to have any technical processes being used unless you have a project that it belongs to. And that project will not exist unless you have an organization that needs the project to create a system of interest. And so there is an aspect of management being very important for our system engineering processes to occur in. But one of the things I don't want us to get too involved in, because program management's fine. I mean, it's been around decades before system engineering got codified. And so I think in the management realm, they're very intense. They know what needs to be done. I'm more concerned about what about that what about the solution area, the design area. And so if you look at the System Engineering Handbook, there's about 3 or 4 processes, right? Your stakeholder requirements, your requirements analysis, and your actual architecture and design processes. Those are where the solution falls out. And I just think that we need to concentrate on those to be sure that we're coming up with a better solution regimen, especially having some kind of science behind us would be nice. Jeff Condra says, what do you see as the impact of system engineering in the energy industry? And actually that comes back to what I was saying about legacy systems, that the energy industry's been with us for 100 years, right, in terms of alternating current. and things like that. So are we going to continue that as an energy thing? And if so, what does that mean? And is there alternatives that can come into play within the infrastructure we have? So I think system engineering can actually play well. And Jeff said, no confirmation you received this, but, oh, okay. Oil and gas industry is what he was hoping to address. And that's true. Even gas and oil would have to be worked. Phyllis Merbeck asked, we have a working group for Agile and system engineering. That's good. That is defining both the need for a modular architecture for the Agile system and the need for practices and processes that define system engineering to flow to help the work in an iterative fashion. That's great. Would you agree to have that we have our eye on the future to address your bad, ugly points? Yes, I do. And Phyllis, I'm glad to see. And that's one nice thing that INCOSE has done with this 2020 vision is they understand they do need to have working groups to address certain aspects of it in order to push either the processes or the technology or the profession into those areas. So they are important. Paul Alberti, he says, I think I said that wrong, sorry, but Paul, he says, do you have any ideas of how information could be collected to actually qualify system engineering success and progress? No, I know what you mean. You're like, what are the metrics of success that would actually work in our favor? And I think that's where you have to put that up front as you're trying to come up with your system as we're working with it. Okay, Andrew, just a few more, and then I think you want to try to wrap up, right?
Yes, that's fine. If you keep on going through the questions, that's fine.
All right. So Julia Johnson, I think I missed Andrew Smith here. Thank you for your thoughts. I can really see and understand the need for lean systems engineering to stop people from seeing system engineering being expensive and cumbersome. What one thing would make the biggest difference and would help to start on that journey? Thank you, Andrew. Actually, lean system engineering is in the system engineering handbook. They talk to it. Again, lean system engineering is applying this lean system, lean thinking in terms of getting rid of non-valued type. You're looking for getting rid of waste and things like that. So anything that doesn't add value, you get rid of. So that's part of the process of making people, I think one of the journey to that is to make people who are implementing these processes tailor them in such a way the value is there. And then lean system engineering, of course, is one of the aspects that they would take into account. So very good point. Julie Johnson asks, which of the following two items currently limits our ability to produce complex systems products predictably? That's true. Limits to capabilities of human system engineering, or the current limitation of tools, info, handling, integration of info across discipline, underlying systems, science, and lack of comprehensive modeling. And Julie, your B actually is where I think our true challenge is trying to bring in the human aspects into the tools and information handling and system science. And it's even interesting as you're talking about like comprehensive modeling, all that requires some kind of human interaction to think through the entire modeling process of what's being brought into play. And you can imagine these complex systems make that very difficult. And I think system sciences can lead the way, but it's a long trudge. And even as they're coming up with system science kind of aspects, that needs to be codified into some kind of education, right? We need to start teaching our system engineers to start using these sciences. What about the system engineers that are already in the workforce? So we do need to kind of have that two-pronged approach of teaching new system engineers as well as old system engineers. Okay, I have two more questions here, and then we can wrap this up. John Mullabert says, how does system engineering future overcome the obstacles imposed by politicians making decisions and defining a problem, how to solve it, which causes the failure of system engineering knew how to prevent? And that's actually a point where you have to start making system engineering a profession that is respected within the politician realm. And so the politicians wouldn't just say, oh, we need scientists to look at this, or we need some psychologists, or we need some, analyst type thing. What about bringing system engineers involved? And I think INCOSE would do well to try to start implementing that type of connection and that type of collaboration with politicians. Last question, Brian Hendrick asked, complexity and emergence. While reductionist approaches are useful, we must also consider the approach of utility and requirements that are less focused on the system-level spec compliance and more focused on characteristic capability, for instance, system-of-system level performance to include degraded modes of operation, true, and sensitivities off normal operating conditions. If we can't test it, we don't know what we're delivering to the user, and that's so true. So that's where I think, again, Brian, one of the keys of this reductionist approach and understanding the aspects of all the components is fine, but when you bring them together, that's where the modeling makes sense. Almost all the work that people understand and work through for complex systems is because they've seen it before. And it's like, okay, I've seen that work, let's try to work the same scenario. And of course, if you have good modeling, that indeed can take place. Thank you for your time. Thank you for your questions. One thing I hope is I kind of inspired you to think about this more. One nice thing about these vision documents that when you start looking at them, they start getting more philosophical. What does it mean to be a system engineer? What does the profession mean to the world? And so I appreciate the ability to be able to talk with you. Hope I didn't bore you too much, but either way, thank you for staying with me during this whole time. Andrew, I'll give it back to you.
Thank you again, Paul, for a great talk. And thank you to the audience for your questions, your time, and such an active chat line. I've never seen such an active one in a webinar. So, Paul, you obviously stirred a lot of thoughts here. The next slide shows our upcoming schedule. The next webinar will be held on Wednesday, the 19th of March 2014, when David Long will present an introduction to INCOSE, which will be an update of the very first webinar from the start of the series. On Wednesday, the 16th of April 2014, Joe Bobinis will present on Design for Affordability. Additional webinars will be offered on the third Wednesday of each month through 2014. Please note that if you go to the website shown here, you'll see more information about the webinar series, including a way to view the last 60 webinars, and soon this webinar as well. I'd like to draw your attention to two upcoming meetings: the Conference on Systems Engineering Research, which will be held in Redondo Beach, California on 21st and 22nd of March 2014, and the Washington Metropolitan Area SEDC Conference, which will be held in Chantilly, Virginia on 3rd to 5th of April 2014. I'd also like to draw your attention to two upcoming paper submission deadlines. 9th of April 2014 for the Complex Systems Design and Management Conference to be held in Paris on the 12th to the 14th of November 2014, and 21st of April 2014 for the Europe, Middle East and Africa Systems Engineering Conference to be held in Cape Town on 27th to 30th of October 2014. As mentioned earlier, you can now claim 1 PDU credit towards your Systems Engineering Professional Recertification by attending this webinar. You may also claim this credit retrospectively for INCOSE webinars that you have attended and where attendance meets the qualification requirements. Please contact INCOSE if you wish to know which webinars you attended and if you met the qualification requirements. Here are some links to find out more about information on the INCOSE Professional Certification Program. Thank you again, and goodbye.